A strange earthquake near Las Vegas has left many people wondering what is really happening beneath the desert. The city may look calm on the surface, but deep below, ancient faults, buried stress, and moving seismic waves tell a much quieter story. In this video, the unusual Las Vegas earthquake is explored step by step, from the desert surface to the hidden rocks beneath it, before starting. Please like this video and subscribe to the channel for more calm science documentaries about the Earth, space, and the mysteries beneath ordinary places. Las Vegas rests in a wide desert basin where the land appears still for long stretches of time. The city spreads across a pale floor of gravel, sand, asphalt, and concrete, with mountains rising in broken lines around the edges. In daylight, the surface often looks hard and dry, shaped by heat, wind, flash floods, and long intervals without rain. At night, the same surface holds the lights of streets, hotels, homes, airports, and highways. It seems steady because daily life depends on steadiness. The desert floor carries traffic, water pipes, power lines, and the quiet weight of neighborhoods. Yet the ground is not a fixed platform. It is the upper skin of a region that moves slowly, usually too slowly for the body to notice. An unusual earthquake near Las Vegas draws attention because the city is more often imagined through light, heat, and distance than through shaking ground. On this outer layer, an earthquake becomes a felt event. A hanging lamp shifts, a window gives a brief sound, a seated person senses a small sideways motion, or a sharper jolt, or only a faint unease that passes before it can be named. The desert itself gives few dramatic signs. It passes through the basin as waves of motion. And then the scene settles back into its familiar shape. The Las Vegas Valley is a basin, a low area partly filled by sediments washed down from surrounding mountains. Sediment means loose or layered material, such as sand, silt, gravel, and clay, that has been carried and deposited by water, wind, or gravity. Across the valley, these materials lie beneath roads and buildings in uneven thicknesses. On the surface, they make broad fans that slope gently away from the mountain fronts. These fans are called alluvial fans because they are built by flowing water that spreads out and drops rock fragments when it leaves steeper ground. They look quiet in dry weather, but they record many older moments when stormwater moved sand and stone from high slopes into the basin. The outer landscape helps explain why a moderate earthquake can become a public subject even when damage is limited. Las Vegas contains dense built areas beside open desert, and the contrast makes shaking easier to compare. In one place, a small movement is noticed inside a hotel room above a busy street. In another, the same motion passes across a vacant wash with no witness except instruments. A person indoors may feel the building respond more than the soil itself. A person outdoors may see no change at all. Reports collect unevenly because people, structures, and instruments are unevenly spread across the basin. The earthquake is one physical event with many surface forms. The valley is bordered by ranges whose shapes are part of the visible setting. The Spring Mountains stand to the west and northwest, with slopes that can hold snow in winter. Frenchman Mountain and Sunrise Mountain rise to the east, closer to the edge of the developed basin. The McCullough Range lies toward the south, while other desert hills and ridges mark the wider horizon. These mountains frame the basin and influence the paths of roads, drainage, settlement, and sightlines. From the valley floor, the mountains make the city feel enclosed. Though the enclosure is wide, the ground seems open and level in the middle, then lifts at the margins into rock. In calm weather, The desert surface carries small, ordinary movements. Wind pushes dust along curbs and open lots. Heat causes materials to expand during the day and cool after sunset. Trucks send vibrations through roads. Construction equipment shakes the ground in a narrow, local way. These motions are not earthquakes, but they are part of the sensory background of an urban desert. An earthquake is different because its motion begins in the earth and spreads across a larger area. Still, at the surface, it may arrive among other small vibrations. This is one reason people ask questions after a short tremor. The body feels motion before the mind has a source for it. When an earthquake is felt in Las Vegas, the first public map is often a map of sensation. Reports appear from neighborhoods, offices, casinos, apartment towers, and communities on the valley edge. Some describe light shaking, some describe a single bump, some describe nothing at all. Scientific agencies collect these reports because they help show how shaking varies across the surface. The reports are not a substitute for instruments, but they add a human layer to the record. In a city built for constant activity, even a small natural motion can stand out because it is not controlled by traffic lights, elevators, or the measured schedule of urban life. The outer region includes the built skin of the city as much as the desert skin beneath it. Pavement covers soil. Foundations press into prepared ground. Storm channels guide runoff away from streets. Utility lines cross the basin below the surface. Airport runways, parking structures, stadiums, homes, and hotels all rest on a landscape that was shaped before the city grew across it. The surface is both natural and engineered. It has been graded, cut, filled, compacted, drained, paved, and landscaped. Even so, the earthquake wave does not recognize the border between a vacant desert lot and a city block. It travels through the ground, then into the things attached to the ground. The unusual quality of a Las Vegas earthquake comes partly from expectation. Many people associate earthquakes with coastal California, the San Andreas Fault, or the western edge of the continent. Southern Nevada feels inland and dry, removed from the common image of earthquake country. But earthquake country is not limited to coastlines. On the outer surface, the region's long history appears as basins, ranges, scarps, tilted blocks, and scattered tremors. The city occupies one part of that wider pattern, even when most days pass without noticeable shaking. At the surface, there is clear boundary between observation and uncertainty. Observations can show where shaking is reported, how strong it appears to be in different areas, and whether damage is seen. They can show whether seismometers, instruments that measure ground motion, record the event. What they cannot show from the surface alone is every detail of the hidden process below. The outer landscape receives the event and leaves other parts unseen. The desert basin is a broad surface where a brief motion becomes noticeable, measurable, and, for a time, discussed. Southern Nevada occupies a wide part of the interior American West, where earthquake activity is less famous than in coastal California, but still belongs to the natural behavior of the region. Las Vegas sits within this larger setting, surrounded by desert basins, mountain ranges, dry valleys, and long roads that cross land shaped by slow movement. The surface appears quiet because most motion happens over spans far longer than a human lifetime. The crust shifts by small amounts. Strain collects over time, and earthquakes occur when part of that strain is released. In this regional view, a Las Vegas earthquake is not isolated from the surrounding land. It belongs to a broad zone where the earth has been stretched, broken, lifted, lowered, and adjusted through time. Nevada is one of the more seismically active states in the United States, even though its earthquakes are often scattered rather than concentrated along one single, famous break. Seismicity means the occurrence and distribution of earthquakes across an area. In Nevada, this distribution reflects a crust that is not moving as one solid plate in a simple way. Instead, many blocks of crust respond to forces around them. Some blocks tilt, some drop, some rise. Some slide past one another along faults. The result is a pattern of earthquake activity that can appear irregular on a map, with clusters in some places and long quiet intervals in others. Las Vegas lies in the southern part of this regional pattern. It is not located on the most active parts of Nevada's earthquake belts, but it is not outside the reach of seismic motion. Earthquakes from nearby areas can be felt in the city, and smaller local events can also draw attention when they occur near populated neighborhoods. The difference between common activity and noticeable activity is important. Many earthquakes are too small or too distant to be felt. Instruments record them, but people do not. When a quake is shallow enough, close enough, or strong enough, it passes from a recorded event into a shared experience. The regional setting is shaped by the basin and range landscape, a large province that extends across much of Nevada and into neighboring states. A province, in this sense, is a broad area with a shared geologic character. The land is marked by alternating mountains and basins, often lined up in long north to south trends. From a distance, this pattern gives Nevada its repeated rhythm of ridge and valley. The mountains are not random ornaments on the desert. They are raised and exposed blocks of crust. The valleys are lower areas partly filled with sediment. The pattern reflects long-term stretching of the crust across the region. This stretching is not a sudden event. It takes place over millions of years, far beyond the scale of a single earthquake or a single city. As the crust stretches, it becomes thinner and breaks along faults. A fault is a fracture or zone of fractures where rocks on one side have moved relative to rocks on the other side. Some faults are quiet for long periods, while others produce earthquakes more often. A fault does not need to be visible at the surface to matter. It may be buried beneath sediment, partly covered by younger deposits, or expressed only as a subtle change in landform. In southern Nevada, many faults are known from mapping, instruments, and the shapes of basins and ranges. The regional crust around Las Vegas also carries the imprint of nearby tectonic systems. Tectonics refers to the movement and deformation of Earth's outer shell. To the west, the boundary between the Pacific Plate and the North American Plate helps shape much of the earthquake activity in California. Southern Nevada is inland from that boundary, but it's still influenced by the broader movement of western North America. The effects are spread across a wide zone rather than confined to one narrow line. In this way, Las Vegas is part of a quieter but still active region of crustal adjustment. Across southern Nevada, earthquakes vary in size, depth, and effect. A small earthquake close to the city may be felt more clearly than a larger earthquake far away, because shaking weakens with distance and depends on the path the waves travel. The same event can feel different in different places because the ground beneath each place is not identical. Rock, gravel, basin sediment, and engineered fill can all affect the motion that reaches a building or a person. Regional maps show the broad pattern, but local conditions shape the immediate experience. The regional setting also includes neighboring zones that have produced notable earthquakes in the past. Western and central Nevada have experienced damaging earthquakes, and parts of the state show clear evidence of active faulting. Southern Nevada's earthquake record is quieter by comparison, but quiet does not mean motionless. A long interval without a damaging event is not proof that the ground cannot shake. It means only that, within the period of observation, larger events have been uncommon in that particular area. Scientific understanding separates absence of recent damage from absence of geologic possibility. Around Las Vegas, the desert gives many surface clues about regional processes. Mountain fronts can be steep where faults help make relief. Basin floors can be broad where sediments accumulate. Drainages cut across fans and washes, leaving patterns that reflect both climate and land movement. Some scarps, which are small steps or slopes in the ground, may form when fault movement reaches the surface. Others may form from erosion. Careful mapping is needed to distinguish them. The landscape is read slowly, through rock layers, landforms, instrument records, and age measurements, rather than through a single visible sign. Public attention often focuses on the unusual character of an earthquake near a city known for entertainment, tourism, and heat. The science places that event inside a more ordinary regional frame. Southern Nevada is part of a living crustal system. Living, in this sense, does not mean dramatic or constant. It means that the crust continues to respond to forces acting across the western United States. Most of the time, that response is subtle. At times, it becomes a tremor that people notice. In this outer regional layer, the main facts remain measured and calm. Las Vegas sits within a basin in a tectonically active part of the interior west. Nevada as a whole has a significant earthquake history, though activity is unevenly distributed. Southern Nevada has known faults and recorded earthquakes, but the exact behavior of any single fault through future time cannot be stated with certainty. Observations show that earthquakes can occur in and around the region. They also show that felt shaking near Las Vegas is part of a larger pattern of slow crustal change. The Basin and Range province gives the Las Vegas region its broader geologic shape. It is a vast part of western North America, where the land is arranged in repeated highs and lows, with long mountain ranges separated by broad valleys. The pattern is visible from roads, aircraft, satellite images, and high desert overlooks. A range rises as a line of broken rock. A basin lies beside it as a lower floor of sediment and dry washes. The pattern repeats across Nevada with a steady rhythm. It does not form from one single mountain-building event. It forms from long stretching of the crust, a slow widening that changes the land from within while leaving a surface of ridges, slopes, fans, and valley floors. In this province, the crust has been pulled apart over millions of years. The pulling is not like a clean tear in cloth. It is more like a broad weakening and extension of rock across a large region. As the crust stretches, it cannot remain smooth and unbroken. It fractures along faults, and blocks of rock shift in relation to one another. Some blocks rise or remain high, forming mountain ranges. Other blocks sink or tilt downward, forming basins. The result is a landscape of alternating steps, where high ground and low ground stand beside each other because the crust has been divided into moving pieces. The movement is slow when measured across a human life. It may amount to small changes spread over long time, yet the accumulated effect is large. Mountains are lifted and exposed. Valleys deepen and fill with material eroded from those mountains. The Las Vegas area belongs to the southern part of this province, where desert climate makes the structure easier to see. Sparse vegetation leaves many slopes open, rock layers, fault scarps, alluvial fans, and dry channels remain visible under bright light. The land keeps a record of motion in its shapes, even when no shaking is felt. A common structure in the basin and range is the normal fault. A normal fault is a break where the rock above the fault surface moves downward relative to the rock below. usually during crustal stretching. This motion helps make basins lower and ranges higher. It is called normal not because it is more important than other faults, but because of the way early geologists described the relationship between rock layers and movement. In simple terms, the upper block slides down as the crust is extended. This kind of motion is widespread in stretched regions, and it helps define the basin and range landscape. The mountains around the Las Vegas Valley are not all made in the same way, and they do not all share the same age or structure. Some contain older rocks that were formed in ancient seas, compressed during earlier mountain building episodes, and later exposed by erosion and faulting. Some hold volcanic materials from past eruptions in the wider region. Some show folded and broken layers that record older forces before the basin and range stretching became dominant. The present landscape is therefore layered in time. The visible ridges are part of a recent geologic form built from much older materials. The basins between ranges collect sediment. Rock breaks from high slopes through weathering, which is the gradual breakdown of material by temperature change, water, chemical reactions, and other surface processes. Gravity carries fragments downslope. Short, intense desert storms move gravel and sand through washes. Over time, these materials spread across valley edges and fill low areas. A basin can hold great thicknesses of sediment, even when its surface looks flat and simple. Beneath a dry valley floor, layers may record many cycles of erosion, flooding, drying, and gradual sinking. This basin filling matters because it softens the visual boundary between deep geologic movement and the modern surface. The faulted blocks form the large structure, but sediment drapes and partly hides that structure. A mountain front may show exposed bedrock, while a nearby basin may bury fault traces beneath younger deposits. The landscape is both revealed and concealed. In places, scarps or tilted surfaces show recent movement. In other places, the evidence lies below sediment and must be inferred from mapping, drilling, gravity measurement, seismic instruments, and the arrangement of landforms. The basin and range also changes how distance is felt across Nevada. A traveller crosses one basin, climbs a range, descends into another basin, and repeats the pattern many times. Each basin may feel separate, yet the same structural theme connects them. Las Vegas is one basin within this larger province. Its urban surface is dense, bright, and engineered, but the valley itself follows the regional form. It lies between uplifted areas, receives sediment from surrounding slopes, and rests within a crustal setting that has been stretched and faulted. Earthquakes in such a province do not require a single central source. They may occur on different faults across a wide zone. Some faults are long and mapped clearly, others are shorter, buried, or less well understood. The earthquake pattern can be diffuse, meaning spread out rather than concentrated. This can make an event seem unusual to the public when it happens near a familiar city. In scientific terms, diffuse activity is part of the character of the province. The crust contains many possible places where a strain may be released. The record is built from both felt events and small instrument-detected events. The basin and range setting also places the Las Vegas Valley within a balance of erosion and motion. Mountains rise or remain high while erosion cuts them down. Basins subside or remain low while sediment fills them. These processes happen together. A range can be losing rock at the surface while still standing high because of crustal structure. A basin can be receiving sediment while continuing to hold a lower position. The visible land is not a single frozen result. It is a temporary surface made by competing slow processes. The unusual earthquake that raises questions is therefore set inside a landscape already shaped by movement. The province does not need to produce frequent large earthquakes near Las Vegas for the city to belong to earthquake country. The structure of the land itself shows that movement has occurred and continues in measured ways. The outer ridges and broad basins are the large-scale expression of a crust that has adjusted through stretching. The questions that follow a felt tremor begin on the surface, but the setting that makes those questions reasonable is written across the entire basin and range. At the edge of Las Vegas, the city loosens into suburbs, roads, empty lots, washes, and low desert slopes. The bright center gives way to wider streets, block walls, shopping centers, construction pads, and neighborhoods that reach toward the mountains. This outer urban edge is one of the places where a small or moderate earthquake becomes especially noticeable, because it brings together open ground and daily structures. The desert is close enough to be seen from windows and roadways. The natural surface is partly exposed. The built surface is still expanding. In this zone, the earthquake is not only a point on a regional map, it is a brief motion passing through homes, schools, garages, fences, drainage channels, and graded soil. The suburbs around Las Vegas spread across ground that is not perfectly uniform. Some areas rest on older alluvial fan surfaces, built from gravel and sand washed down from the mountains. Some rest on finer basin deposits that settled in lower parts of the valley. Some areas have been cut, filled, and compacted for construction. The ground may appear level after grading, yet its materials can vary beneath the surface from one block to another. This matters because earthquake shaking is shaped not only by the source of the quake, but also by the ground that carries the motion upward. At the suburban edge, these differences are close to the everyday spaces where people notice movement. A felt earthquake often arrives without visual warning. A person indoors may first notice a vibration in a wall or a faint shifting of furniture. A garage door may rattle, dishes may make a small sound, a hanging object may move slightly. In a single-story house, the motion may feel like a short jolt. In a taller building, it may feel slower or more rolling, depending on the building's design and the kind of waves arriving. Outdoors, the same event may be less obvious. A person walking across a parking lot may feel little or nothing if the motion is weak. A person standing still on a concrete slab may notice more. The felt experience is uneven, even within the same suburb. The edge of the city also includes infrastructure that extends across the valley. Roads cross washes, bridges carry traffic over channels and rail lines. Utility corridors follow open land. Water systems, power lines, communication cables, and gas lines connect neighborhoods to the larger urban network. Most small earthquakes do not damage these systems, but their presence shapes public concern. People ask whether the shaking is a sign of something larger, whether the ground below a neighborhood is different from another, and whether a short tremor has any meaning beyond the moment itself. Science answers these questions by separating what is observed from what is assumed. In the suburban zone, reports of shaking may cluster around places with more people rather than places with stronger motion. A quiet desert wash can shake without producing a public report. A neighborhood with many homes can produce many reports from the same level of ground motion. A hotel corridor, a school building, or a residential tower may lead to more reports because many people feel the motion indoors at once. This creates a human map that is useful but not complete. Scientists compare these reports with seismometer records to understand where shaking was strongest and how it changed across the valley. The outer suburbs lie near mountain fronts in some parts of the valley. These fronts are the transition between higher bedrock and lower sediment-filled ground. The ground may slope gently across fans, then steepen where rock rises. Storm channels cut through these slopes, carrying water only during rare or seasonal flows. Roads and houses cross surfaces that were built by older floods and debris movement. The earthquake passes through this setting as energy. But the landforms give context to what people feel. A house near a rocky slope may rest on different material than a house farther down a fan. A development built on compacted fill may respond differently from an older area on natural sediment. Urban expansion can make the desert edge look new, but the land beneath it holds a longer record. Construction removes some surface clues while revealing others. Grading can smooth small scarps, fill shallow channels, or expose gravel layers. Excavations for foundations and utilities may show beds of sand, clay, or cemented sediment. These are not dramatic signs by themselves. They are ordinary features of the basin edge, yet they remind that a suburb is built onto a landscape with its own structure. The earthquake, when it comes, moves through both the natural deposits and the engineered materials placed above them. A small earthquake near Las Vegas can feel unusual because suburban life is built on repeated routines. The motion interrupts a steady evening, a morning commute, or a quiet night. It may last only seconds, but it changes attention. People look toward windows, phones, pets, hanging lights, or neighbours. The event becomes a subject because it is shared across scattered places. Some feel it clearly, others nearby feel nothing. This difference does not necessarily mean one report is wrong. It shows how human position, building type, ground material, and attention all influence the felt record. At this outer city edge, earthquake science stays practical and careful. Shaking intensity describes how strong the motion feels or how it affects people and structures at a particular place. Magnitude describes the energy released at the source. The two are related, but they are not the same. A moderate magnitude earthquake can produce weak shaking far away or stronger shaking near its source. A small earthquake can be noticed if it occurs close enough. In suburbs near Las Vegas, people often experience the earthquake through intensity first, then learn about magnitude later from agencies and reports. The suburban region also shows the limits of immediate interpretation. A single felt earthquake does not reveal a complete future pattern. It may be followed by smaller aftershocks, or it may not be widely noticed again. It may occur on a known fault system, or its exact relation to mapped structures may need careful study. What can be said at this level is narrower and more dependable. Shaking reaches neighborhoods in different ways. Reports reflect both physical motion and human distribution. Buildings and ground materials shape the experience. The city edge receives the earthquake as a brief disturbance across the meeting place of desert land and built life. Beneath the streets and open lots of the Las Vegas Valley, the near-surface ground is made of many kinds of sediment. This layer sits closer to daily life than the deeper crust, and it can shape the way earthquake motion is felt. Sediment is not one simple material. It can be coarse gravel, loose sand, fine silt, clay, or mixtures of all of them. It can be young and weak, or older and more compacted. It can be dry near the surface as more firmly packed below. Across a desert basin, these differences may change over short distances, even when the surface has been graded smooth for roads and buildings. The valley floor is partly built from material carried down from surrounding mountains. When rain falls hard on desert slopes, water can move quickly through channels and washes. It picks up rock fragments, sand, and finer particles, then spreads them across lower ground as the slope becomes gentler. Over long periods, this process builds alluvial fans. These fans are broad, sloping bodies of sediment that spread outward from mountain fronts. Near the mountain, the material is often coarse, with stones and gravel. Farther from the source, the particles may become smaller. The earthquake wave must pass through these materials before it reaches a house, a road, or a person standing at the surface. In the lower parts of the basin, finer sediment can gather. Silt and clay may settle where water slows or stands for a time. Some layers may come from ancient lakes, temporary ponds, or slow-moving floodwater. Other layers may be wind-blown dust that settles across the valley. These fine deposits behave differently from coarse gravel. They can hold water in different ways. They can compress more easily. They can transmit shaking with different strength and timing to the eye. A paved street hides these contrasts. To seismic waves, the contrasts matter. Seismic waves are vibrations that carry earthquake energy through the earth. As they move upward from deeper rock into softer sediment, their speed can change. When waves slow down in softer material, some shaking can become stronger at the surface. This is called amplification, which means an increase in the size of motion. The effect is not the same everywhere. It depends on the thickness of the sediment, the stiffness of the layers, the kind of waves arriving, and the frequency of the motion. Frequency means how often a vibration repeats in a given time. A slow sway and a sharp rattle are different forms of motion, and different ground layers can favor different kinds. The Las Vegas Basin is not a bowl filled evenly with one material. It is a layered and irregular body of sediment resting between higher blocks of rock. Some areas may have shallow, firm material, while others may contain thicker basin fill. The boundaries between these conditions are not always visible at the surface. Engineers and geologists use drilling, mapping, geophysical measurements, and earthquake recordings to understand them. Geophysical measurements are methods that study the ground through physical properties such as wave speed, density, gravity, or electrical behavior. These methods help reveal what the paved surface cannot show. In an earthquake, the near-surface layer can also affect duration. Hard rock may transmit certain waves quickly and with less trapping. Softer basin sediments may allow waves to bounce, slow, or reverberate within the basin. Reverberation means repeated vibration within a layer or enclosed shape. The effect can make shaking last slightly longer in some areas than in nearby rocky ground. This does not mean every basin earthquake is severe. It means the basin shape and sediment thickness are part of the final motion that people experience. The source starts the earthquake, but the ground near the surface edits its arrival. Some sediment is cemented by minerals, forming harder layers within the basin fill. In desert regions, calcium carbonate and other minerals can collect between particles and bind them together. This can create caliche, a hardened layer common in arid landscapes. Caliche may be thin in one place and thicker in another. It can make digging difficult and can influence shallow foundations. Its effect on earthquake shaking depends on its thickness, depth, and relation to other layers. Like many surface materials, it is only one part of a larger ground profile. Groundwater also plays a role in the behavior of sediment, although its importance depends on depth and local conditions. Groundwater is water stored beneath the surface in pores and fractures. In some earthquake settings, water-saturated loose sand can lose strength during strong shaking, a process called liquefaction. Liquefaction means that wet, loose sediment temporarily behaves more like a fluid because shaking increases pressure between grains. In the Las Vegas Valley, this risk is not uniform, and it depends on local groundwater levels, sediment type, and shaking strength. It is a specific engineering and geologic question, not a single condition applied to the whole basin. Near-surface sediment also influences the difference between what instruments measure and what people feel. A seismometer placed on firm ground may record motion differently from one placed on softer basin fill. A person in a building may feel the combined response of ground and structure. A neighborhood built on thicker soft sediment may experience stronger shaking than another area at the same distance from the earthquake source. But this must be measured rather than assumed. The valley's sedimentary surface creates possibilities that require careful observation. In the quiet days between earthquakes, these sediments continue to change slowly at the surface. Wind moves fine dust. Stormwater shifts sand and gravel in washes. Construction compacts fill and changes drainage. Drying and wetting alter shallow soils. These processes are ordinary parts of desert ground. They do not cause most earthquakes, but they shape the layer through which shaking must pass. The earthquake enters this layer from below and emerges as motion that can be felt in rooms, foundations, and roads. At this sediment level, the unusual Las Vegas earthquake becomes less mysterious and more local. The same regional event does not arrive everywhere in the same way. It travels through a basin with coarse fans, fine deposits, cemented layers, engineered fill, and hidden changes in thickness. Observations can show where shaking is stronger, where it is weaker, and how it compares with nearby rock sites. What remains uncertain without detailed study is the exact contribution of each buried layer at every point in the city. The surface sediments form a quiet, uneven filter between the deeper earthquake and the human experience above. The urban structures of Las Vegas stand on the surface as the most visible receivers of shaking. They include small homes, apartment blocks, hotels, parking garages, schools, bridges, signs, utility poles, stadiums, and long corridors of commercial buildings. Each structure has its own shape, height, weight, age, and foundation. When an earthquake wave reaches the city, the motion does not remain only in the ground. It enters these structures and becomes movement in walls, beams, windows, floors, ceilings, and contents. The same ground motion may feel different inside different buildings because each building responds in its own way. A structure responds to shaking according to its design and materials. Wood frame houses often flex during light to moderate motion. Concrete and steel buildings may sway in ways that depend on their height and stiffness. Masonry walls, especially older unreinforced masonry, can be more vulnerable when shaking is strong enough, because brick or block without adequate steel reinforcement does not bend easily. Reinforcement means added material, often steel, placed to help a structure resist stress. Modern building codes seek to reduce collapse risk and protect life, but buildings from different periods may have different standards, repairs, and hidden conditions. In a small earthquake, the response is often limited to sound and brief motion. A window rattles, a door shifts in its frame, a shelf vibrates, a hanging lamp moves in a small arc. These are not necessarily signs of damage. They are signs that the building is transmitting motion from the ground into its parts. People may feel the movement more strongly indoors than outdoors because the building can amplify or focus certain vibrations. A wall panel or ceiling fixture can make sound even when the ground motion is weak. The building becomes an instrument of attention. The height of a structure affects how it feels during shaking. A low to stiff building may respond with a short jolt. A taller building may sway more slowly, especially if the incoming waves contain periods that match its natural movement. Period means the time it takes for one complete back and forth motion. Every building has natural periods, shaped by its height, mass, and stiffness. When ground motion contains similar periods, the motion inside the building can feel stronger. This does not require a large earthquake in every case. It requires a match between the arriving motion and the way the structure prefers to move. Las Vegas contains many large buildings that are designed for heavy use, high occupancy, and complex systems. Hotels and resorts include towers, podiums, parking structures, mechanical floors, long spans, and decorative elements. Their engineering accounts for wind, gravity, fire safety, and seismic requirements. In light shaking, people high inside a tower may notice a gentle movement that differs from the sharper vibration felt at street level. Elevators may pause or systems may be checked after a noticeable event. These responses are part of cautious management rather than proof of severe damage. Large buildings are monitored and inspected when motion reaches levels of concern. Residential neighborhoods show another kind of structural response. Houses may be built on slabs, crawl spaces, or other foundation types suited to local ground and construction practice. The foundation is the part of the structure that transfers weight into the ground. During shaking, the foundation moves with the soil below it, and the house above responds through its frame. Interior items often reveal the motion first. Pictures shift slightly. Cabinets make noise. A pet reacts to vibration or sound. The structural frame may remain unharmed while the experience feels vivid because it happens inside a familiar private space. Bridges and road structures are also part of the urban layer. Freeways cross the valley, and ramps, overpasses, and retaining walls carry traffic through dense corridors. Modern seismic design aims to keep these structures stable during expected levels of shaking. In a small or moderate event, inspections may focus on joints, bearings, columns, pavement cracks, and signs of settlement. Settlement means downward movement of ground or structure. Most minor earthquakes do not lead to major transportation damage, but the possibility of disruption matters because roads connect emergency response, tourism, work, and daily movement across the valley. Non-structural elements often shape public memory of an earthquake. Non-structural means parts of a building that are not the main load-carrying frame, such as ceiling panels, lights, shelves, pipes, equipment, signs, and decorative facades. These items may move, make noise, or suffer minor damage even when the main structure remains sound. In a city with large signs, glass, lighting systems, and suspended features, the visible response can attract attention. Scientific assessment distinguishes between non-structural movement and structural damage, because the risk and meaning are not the same. The age of construction matters, but age alone is not a complete measure of safety. An older building may have been strengthened. A newer building may have unusual design features requiring careful engineering. A simple building may perform well because its load paths are clear. Load paths are the routes through which forces move from one part of a structure to another and down into the ground. A complex building may need more detailed analysis because forces move through many connected parts. Engineers look at design drawings, materials, inspections, and observed effects rather than relying only on appearance. During and after a felt earthquake, the urban structure layer produces many signals. Some are physical, such as cracks, fallen items, or stuck doors. Some are operational, such as alarms, elevator checks, or temporary closures for inspection. Some are social, such as reports from residents and workers. The science of earthquake effects uses these signals carefully. A crack in plaster may predate the earthquake. A fallen object may reflect poor anchoring rather than strong shaking. A building with no visible effect may still have moved. Each observation has to be placed in context. Las Vegas also has extensive lifelines, meaning systems that support daily life, including water, power, gas, communication, and transportation. These systems depend on pipes, cables, control stations, substations, pumps, and access roads. Earthquake shaking can stress them where lines cross different ground materials or where older connections are brittle. In minor events, lifelines usually continue operating, but they remain part of preparedness planning. The urban structure layer is not only buildings, it is the network that lets the city function. At this level, an unusual earthquake becomes a test of response rather than a sign of collapse. Structures receive the motion, translate it into movement and sound, and then either continue normally or call for inspection. Observations can show where items moved, where people felt swaying, where alarms sounded, and where no effect occurred. They can also show whether building performance matches expectations. What remains uncertain without careful inspection is the condition of every hidden connection, foundation detail, or older material. The earthquake passes quickly, but the built environment holds the evidence long enough for measured review. Seismic waves are the moving energy of an earthquake. They begin when rock breaks or slips along a fault, then travel outward through the earth and across the surface. In the Las Vegas region, these waves pass through desert crust, basin sediments, and urban structures before they become the motion that people notice. At the level of the waves themselves, an earthquake is not one simple shake. It is a set of different motions arriving at different times, with different speeds, directions, and effects. Some waves move through the body of the earth, some move along the surface. Together, they form the pattern recorded by instruments and felt by people. The first waves to arrive are usually primary waves. A primary wave is a compressional wave, meaning it pushes and pulls material in the same direction that the wave travels. It can move through solid rock and also through fluids. Because it travels quickly, it often reaches a seismometer before other waves. For a person near an earthquake, it may feel like a quick bump or a faint vibration. It may also go unnoticed if the event is small or distant. Primary waves carry important information because their arrival time helps scientists estimate the location of the earthquake. Secondary waves usually arrive after primary waves. A secondary wave moves material side to side or up and down at right angles to the direction the wave travels. It moves through solid material but not through liquid. Secondary waves are generally slower than primary waves, but they often produce stronger shaking for people and structures. In a desert basin, they can enter sediment and interact with layers of different stiffness. The change from harder rock to softer sediment can alter the wave's speed and motion. This is one reason shaking may vary across the Las Vegas Valley. Surface waves travel along or near the outer part of the Earth. They often arrive after the body waves and can create rolling or side-to-side motion. Surface waves can be important in felt shaking, especially at greater distances from larger earthquakes. They may move through the basin in a way that is shaped by the ground beneath the city. A surface wave does not need to be visible at the ground like an ocean wave. It is a motion passing through solid earth, bending roads, buildings, and soil by very small amounts during weak shaking and by larger amounts during stronger events. The path of seismic waves matters. A wave travelling through hard, continuous rock may keep a different character from a wave crossing broken rock, basin fill, or layers with strong contrasts. The Las Vegas Valley includes both bedrock edges and thick sediment in lower areas. As waves enter these materials, they can bend, reflect, scatter, or slow. Reflection means a wave bounces from a boundary between materials. Scattering means energy is redirected by irregular structures in the ground. These processes do not create the earthquake, but they help decide how the earthquake is experienced at the surface. The size of emotion also changes with distance. In general, shaking weakens as waves spread outward from their source. The energy is distributed over a larger area, and some of it is absorbed by the materials it passes through. Absorption, in this setting, means the conversion of wave energy into small amounts of heat and internal movement within the rock or sediment. The rate of weakening is not the same everywhere. Some paths carry energy more efficiently. Some materials reduce high-frequency motion faster than low-frequency motion. High-frequency motion feels like rapid vibration. Low-frequency motion feels slower, sometimes like swaying. A seismogram is the recorded trace of ground motion from a seismometer. It shows arrivals, amplitudes, and durations. Amplitude means the size of the recorded motion. A small earthquake produces a small trace, though the shape can still reveal clear wave arrivals. By comparing the arrival times of primary and secondary waves at several stations, scientists locate the source. The greater the time gap between the first primary wave and the first secondary wave at one station, the farther that station is from the earthquake. With records from many stations, the location becomes better constrained. For people in Las Vegas, the wave sequence may be too brief or subtle to separate. A primary wave, a secondary wave, and surface waves may blend into one short experience. Someone may describe a jolt because the early motion is sharp. Someone else may describe a rolling feeling because the building or ground responds to longer period motion. These descriptions are not always contradictions. They reflect different positions, structures, ground materials, and attention. The same earthquake can have several felt forms because the wave field is complex by the time it reaches the surface. The depth of the source also shapes the waves, but at this section's level the focus remains on their travel. Waves from a shallow source have less distance to travel before reaching nearby surface locations, so their high-frequency energy can remain clear. Waves from a deeper source travel longer paths through the crust before reaching the surface. In both cases, the arriving motion is shaped by the source, the travel path, and the site conditions. Site conditions are the local ground properties at a particular place. In the Las Vegas basin, site conditions may shift from firm fan gravel to softer fine sediment within the developed valley. Seismic waves also explain why an earthquake can be heard as well as felt. Some shaking enters buildings and makes objects vibrate within the range of human hearing. The sound does not mean the ground itself is making a large noise everywhere. It often means that walls, glass, furniture, ducts, shelves, or fixtures are responding to motion. A small tremor may be remembered more for its sound than its movement. The body senses vibration, and the ear receives the building's reply. Instruments separate what human senses combine. They record motion in precise directions, often vertical and two horizontal components. A component is one measured direction of movement. This helps scientists understand whether motion was mostly up and down, side to side, or a mixture. The record can be processed to estimate intensity, magnitude, and source properties. These calculations rely on physics and careful calibration, not on public surprise. The unusual feeling of an earthquake near Las Vegas becomes clearer when translated into wave arrivals and measured ground motion. At the wave level, the event is a passage of energy through a layered region. Primary waves arrive first, secondary waves follow, and surface waves may carry motion along the upper earth. Their speeds, paths, and interactions with sediment and rock shape what is felt across the valley. Observations can identify arrivals and measure amplitudes. What remains uncertain in the immediate aftermath is the full detail of every path the waves take through buried structures beneath each neighborhood. The waves move quickly, but the understanding of their journey is built slowly from records. Local fault systems form a more hidden layer beneath the Las Vegas region. At the surface, the city appears as a spread of streets and desert slopes, but below and around it the crust is crossed by breaks and zones of weakness. A fault is not always one clean crack. It can be a narrow surface, a set of connected fractures, or a wider zone where rocks have moved in more than one episode. Some faults are mapped clearly because they leave marks on the land. Others are buried beneath basin sediment and are known from geologic studies, instrument records, or the shape of the valley itself. Near Las Vegas, the fault pattern belongs to the broader basin and range setting, but it also has local details. The valley is bordered and crossed by structures that reflect extension, shifting blocks, and older episodes of deformation. These faults do not all move at the same rate, and they do not all have the same history. Some may show evidence of relatively recent geologic movement. Some may be older features that remain weak but have not produced known surface-breaking earthquakes in recent time. The map is therefore not a simple pattern of active and inactive lines. It is a layered record of motion, uncertainty, and observation. Fault mapping begins with a surface where evidence is visible. A fault may create a scarp, a small step or slope where the ground has moved. It may offset an alluvial fan, bend a drainage, place older rock against younger sediment, or form a straight mountain front. These signs must be interpreted carefully because erosion, deposition, and human grading can alter the surface. A slope may look fault-related but come from water cutting into sediment. A fault may be real but hidden by younger deposits. Geologists compare landforms, rock types, sediment ages, and subsurface information before drawing conclusions. The Las Vegas Valley contains several mapped fault zones and nearby structural features. Some lie along basin margins, where mountains meet sediment-filled low ground. Others are closer to the interior of the valley or within the wider surrounding region. Their exact relationships to any single small earthquake may not be immediately clear. A quake can occur on a mapped fault, on a small branch of a known system, or on a buried structure that has not been traced at the surface. For this reason, scientific agencies often begin with the earthquake's location, depth, and focal mechanism before assigning it to a specific fault, if such an assignment is justified. A focal mechanism is a scientific estimate of the type of fault motion during an earthquake. It is based on the first motions recorded by seismometers at different stations. It can suggest whether the fault slipped mainly by extension, compression, or sideways movement. In a region like southern Nevada, many earthquakes are associated with normal faulting, which fits crustal stretching, but local motions can be more complex. The mechanism helps connect a felt event to the structure of the crust. Yet it does not always identify the exact fault plane, because two possible planes can often fit the same data. Faults store strain when rocks on either side are held by friction while broader forces continue to act. Friction is resistance to sliding between surfaces. The rocks may be pressed together strongly, and the fault may remain locked for a long time. Stress builds slowly. When the stress overcomes friction and the strength of the rocks, slip occurs. This slip sends seismic waves outward. The fault itself may move by only a small amount in a minor earthquake. Yet the energy is enough to be recorded and sometimes felt. The fault is the place where stored strain turns into motion. Local fault systems also explain why earthquakes can occur in clusters. A small slip can slightly change the stress nearby. That change may encourage or discourage slip on neighbouring parts of a fault or on nearby fractures. This does not mean that every small earthquake leads to a larger one. Most do not. It means that the crust behaves as a connected system, and each event is part of a stress field rather than an isolated point. In the Las Vegas region, small earthquakes may appear scattered because the faults are numerous, partly buried, and unevenly active. The age of fault movement is important for hazard assessment. A fault that has moved in the recent geologic past is generally more important than one with only ancient movement. Recent, in geology, can still mean thousands or tens of thousands of years. Scientists may study sediments cut by a fault to estimate when movement occurred. They may dig trenches across a scarp, examine layers, and date materials above and below the displacement. This work is slow and careful. It does not turn every fault into an immediate danger. It builds a longer record of what the fault has done. In a city setting, local faults can be difficult to study because roads, buildings, and grading cover natural surfaces. Urban development may hide subtle scarps or disturb shallow deposits. At the same time, construction, drilling, and engineering studies can reveal subsurface information that would otherwise remain unseen. The urban landscape both conceals and exposes parts of the fault record. Scientific understanding depends on combining many kinds of evidence rather than relying on a single visible trace. A local earthquake near Las Vegas can therefore raise questions because the fault beneath it may not be obvious to residents. The ground shakes, but the responsible surface feature may not be visible from a street or window. A person may look at flat pavement and see no sign of the structure below. This is normal in sediment-filled basins. Faults can lie under alluvium, beneath neighbourhoods, or along mountain fronts where their evidence is partly softened by erosion and deposition. The lack of a visible crack after a small earthquake does not mean there is no fault. It often means the slip remains deep or small enough not to rupture the surface. At the local fault level, the earthquake is no longer only a felt motion or a travelling wave. It is tied to a break in rock where stress has been released. Observations can locate the event, estimate the kind of motion, and compare it with known mapped structures. They can show whether aftershocks align along a possible fault zone. What remains uncertain without detailed analysis is the full geometry of every buried fracture and its long-term behaviour. The local fault systems beneath and around Las Vegas are part of a slow, complex crustal pattern, mostly quiet at the surface, but capable of producing motion that briefly reaches the city above. Earthquake depth is one of the quiet details that shapes how a tremor is felt. It is not as easy to picture as a cracked road, a moving lamp, or a line on a map, yet it strongly affects the experience at the surface. Depth means the distance from the surface down to the place where the earthquake begins. This starting point is called the hypocenter, or focus. The point on the surface directly above it is called the epicenter. The epicenter is often the location most people hear first. But the depth gives the event its vertical position within the crust. A shallow earthquake starts close to the surface. A deeper one starts farther below, even if its surface location is the same. In the Las Vegas region, shallow earthquakes can attract attention because their energy has less distance to travel before reaching nearby people, buildings, and instruments. The shorter path can preserve sharper motion, especially the faster vibrations that make objects rattle and walls sound. A small, shallow event may feel surprisingly clear to those nearby, while a larger but more distant or deeper event may feel softer. This does not mean shallow earthquakes are always damaging. It means that depth is part of the relationship between energy released below and motion felt above. The ground does not respond only to magnitude, it responds to magnitude, distance, depth, wave path, and local ground conditions together. The crust beneath southern Nevada is not uniform. It contains older rock, fault zones, basin fill, fractures, and changes in temperature and pressure with depth. Earthquakes in the upper crust usually occur where rocks are brittle enough to break. Brittle means that material fractures rather than flowing smoothly. Near the surface and through much of the upper crust, rocks can store stress until they slip suddenly. Deeper down, rising temperature and pressure gradually change how rocks deform. Some rocks still break at depth, but in many settings the deeper crust becomes more likely to bend or flow slowly rather than fracture in the same sudden way. The depths of earthquakes therefore reveal something about where brittle behavior is present. A shallow earthquake near an urban basin may feel abrupt because its waves reach the surface quickly. The first motion may come as a single thud or snap-like vibration. This impression is created by the wave arrivals and the response of the building or ground, not by the earthquake needing to be large. People often describe shallow local events as sharp because the higher frequency energy remains stronger close to the source. High frequency energy produces rapid motion. It can shake windows, shelves, and small objects. Lower frequency energy produces slower motion and may be noticed more in taller structures. The depth of the source helps determine how much of each kind reaches the surface nearby. The determination of depth comes from seismic records. Instruments at different stations record the arrival times and shapes of waves. Scientists compare these times with models of how fast waves travel through the crust. A model, in this setting, is a simplified representation of underground structure used for calculations. If the wave speeds are well known and the station coverage is good, the depth estimate can be more precise. If stations are sparse, the earthquake is small, or the underground structure is complex. Depth can be harder to determine. For small events, early depth estimates may be revised as more data are processed. Depth uncertainty is important. A reported depth is not always an exact point without error. It may carry a range of possible values, especially soon after the event. A shallow depth can sometimes be fixed by the data. In other cases, the solution may be influenced by assumptions in the velocity model or by the geometry of recording stations. This is why scientific agencies update earthquake information. The first public number is useful, but it may not be final. A calm interpretation allows for revision without treating the change as unusual. Earthquake locations and depths improve as records are reviewed. For a person in Las Vegas, depth matters most through its effect on intensity. Intensity describes the strength of shaking at a particular place, as observed by people, objects, structures, and instruments. A shallow earthquake under or near the valley may produce a small zone of more noticeable shaking close to the epicenter. Farther away, the motion may fade quickly. A deeper earthquake may be felt over a broader area but with less sharpness near the surface, depending on its size and path. The pattern is not fixed, because rock type, basin shape, and wave direction also matter. Still, the general relationship between shallow depth and clearer local shaking is well established. The source depth also affects whether an earthquake can break the surface. Most small and moderate earthquakes do not create visible ground rupture. Their slip remains confined below the surface, or the displacement is too small to reach and mark the land. A shallow event is closer to the surface, but closeness alone does not guarantee rupture. The earthquake must be large enough, the fault must extend upward in the right way, and the slip must be sufficient. in a sediment-filled basin. Even some near-surface deformation may be softened or hidden by loose material. After a small event, the absence of a visible crack is ordinary. Depth connects the human moment to the structure of the crust. A person feels a jolt in a room, while the source may lie several kilometers below, within a volume of rock under stress. The distance is small on a planetary scale and large on a human one. Between the source and the surface are layers of rock and sediment that change the motion. This vertical path is as important as the horizontal distance from the epicenter. Two locations the same distance from the epicenter may feel different if the waves rise through different materials or enter different structures. In the Las Vegas area, public questions after an unusual earthquake often focus on why it felt strong, why it was brief, or why it was noticed in one neighborhood and not another. Depth is one part of that answer. A shallow event can make a small earthquake feel immediate. It can produce short, sharp shaking near the source. It can also be recorded clearly by nearby instruments. Yet depth alone does not explain every report. It works with magnitude, fault motion, wave direction, basin sediment, and the built environment. At this inner level, the earthquake is placed within the vertical dimension of the crust. Observations can estimate where the rupture begins below the surface and how that depth shapes the arriving waves. They can show whether an event is shallow enough to explain concentrated local shaking. What remains uncertain without detailed analysis is the exact three-dimensional path from source to each felt location. The depth gives the earthquake its hidden position, and from that position the motion travels upward into the valley, brief enough to pass in seconds, clear enough to leave questions behind. Earthquake swarms and aftershocks form a deeper pattern of repeated motion within a faulted region. A single earthquake may be the event people notice, but it can occur within a sequence of smaller events before or after the felt shaking. An aftershock is an earthquake that follows a larger earthquake in the same general area as the crust adjusts to change stress. A swarm is a group of earthquakes that occur close together in time and space without one clear main event dominating the sequence. These patterns are common in many tectonic regions, including parts of Nevada, and they require careful interpretation because repeated earthquakes can sound more meaningful to the public than they are in strict scientific terms. In the Las Vegas region, a cluster of small earthquakes can attract attention because it appears to disturb the usual quiet of the city. People may notice one tremor, then hear that instruments recorded several more. The repeated signals may seem to suggest that the ground is preparing for a larger event. Scientific understanding is more cautious. Small earthquakes show that stress is being released on faults or fractures, but they do not provide a reliable prediction of a larger earthquake. Most small earthquakes are not followed by damaging events. Some larger earthquakes do have foreshocks, which are smaller earthquakes before a main event, but they can usually be recognized as foreshocks only after the larger event has already happened. Aftershocks follow statistical patterns, but they do not follow a schedule that can be known in advance. In many sequences, the number of aftershocks decreases with time. The largest aftershock is usually smaller than the main event, though it may still be felt if it is close and shallow. This pattern reflects the crust settling into a new stress arrangement after the first slip. The main rupture changes the forces on nearby parts of the fault system. Some parts are brought closer to failure. Others may be relieved. The result is a fading series of smaller adjustments, though the exact timing and size of individual aftershocks remain uncertain. A swarm has a different character. Instead of one event clearly standing above the rest, many small earthquakes occur within a limited area over hours, days, weeks, or longer. Swarms can be related to stress changes, fault complexity, fluid movement in rock, or volcanic systems in some regions. Around Las Vegas, interpretation depends on location, depth, waveform patterns, and geologic setting. A swarm in a tectonic fault zone is not the same as a swarm near an active volcano. The word itself describes the pattern of events, not a single cause. Scientists examine the data before assigning meaning. The instruments that record these repeated events can detect many earthquakes too small for people to feel. This creates a difference between public experience and scientific record. A person may feel one tremor, while a seismic catalogue lists several small events around it. The catalogue is not exaggerating the shaking. It is showing that the Earth moves at levels below human sensation. A magnitude too small to be felt can still help define a fault trend, or reveal how stress is being released. These quiet records are important because they give context to the event that reaches public attention. Repeated earthquakes are located by comparing wave arrivals at multiple stations. When several events occur close together, scientists may use their similarities to improve locations. Earthquakes on the same small fault patch can produce similar waveforms, because waves leave from nearly the same place and follow nearly the same paths. A waveform is the shape of recorded ground motion over time. Similar waveforms can help identify related events. This method may show whether a sequence lines up along a fault plane or spreads through a volume of fractured rock. The pattern helps distinguish a simple aftershock sequence from a more diffuse swarm. Depth is also important in sequences. If repeated events occur at similar depths, they may reflect slip within the same brittle layer of crust. If depths vary widely, the sequence may involve a more complex structure or may include greater uncertainty in location. Small earthquakes can be difficult to locate precisely, so scientists treat the pattern with measured care. A cluster that appears broad on an early map may become tighter after review. A sequence that appears tied to one fault may later be understood as more distributed. The record improves as more data are processed. Public concern often grows when repeated shaking is felt over a short period. The mind looks for order in the sequence. It asks whether the first event was a warning, whether the later events are building, or whether the pattern is abnormal. Earthquake science can answer some of these concerns, but not all. It can estimate probabilities over time. It can identify whether aftershocks are expected after a main event. It can compare a sequence with known regional behavior. It cannot name the exact time, place, and magnitude of a future damaging earthquake. This boundary between probability and prediction is central. In the Las Vegas area, the unusual nature of a felt earthquake may come from rarity in public memory rather than rarity in the instrument record. A city may go long periods without a widely noticed tremor, while small earthquakes continue in the broader region. When a felt event is followed by small recorded aftershocks, the sequence becomes visible to the public. The scientific meaning is not panic, it is documentation. Each event adds information about where the crust is slipping, how stress is changing, and how local faults behave. Aftershock forecasts may be issued after significant earthquakes in some regions. These forecasts describe the likelihood of additional events within certain magnitude ranges and time periods. They are based on observed patterns from many earthquake sequences. They are not guarantees. A low probability event can still occur, and a high probability of small aftershocks does not mean a damaging earthquake will follow. Forecasting is a way of expressing uncertainty with numbers. It helps emergency managers and the public understand that risk changes after an earthquake, then usually declines with time. At the level of swarms and aftershocks, the earthquake is part of a sequence rather than a lone point. Observations can show whether small events are clustering, fading, or migrating through a faulted area. They can distinguish many events that people never feel from the few that reach the surface as noticeable shaking. What remains uncertain is the exact future path of a sequence while it is still unfolding. The repeated signals beneath and around Las Vegas are measured carefully, interpreted within known physics, and held within the limits of what earthquake science can and cannot predict. The Nevada test site, now known as the Nevada National Security Site, lies to the northwest of Las Vegas within a broad desert region that has a distinct place in the public memory. During the 20th century, this area was used for underground nuclear testing, and those tests created ground motion that could be recorded by instruments and sometimes felt at the surface. The presence of this history adds a layer of attention whenever an earthquake occurs in southern Nevada. People may recall that controlled underground explosions once took place within the same general region, and they may ask whether a present-day tremor could be related. At the scientific level, the distinction between a natural earthquake and a human-made explosion is clear, but it requires explanation grounded in observation. An underground nuclear test produces seismic waves because it releases energy suddenly within the Earth, much like an earthquake. However, the physical process is different. An explosion pushes outward in all directions from a point, while an earthquake usually involves slip along a fault, where rocks move past one another along a surface. This difference in source process creates differences in the seismic signals that instruments record. The first motions, the balance between compressional and shear waves, and the overall waveform pattern can help scientists identify the origin of the event. Over decades of monitoring, these distinctions have been studied in detail. Primary waves generated by an explosion tend to be relatively strong compared with secondary waves, because the initial motion is outward compression. In contrast, earthquakes often generate stronger secondary waves relative to primary waves because of the sideways motion along a fault. Surface waves also differ in their characteristics between the two types of events. By examining these differences across multiple stations, scientists can determine whether a recorded signal is consistent with a natural earthquake or an explosion. This analysis does not depend on a single station or a single measurement. It uses a network of observations. Location is another key factor. The sites used for past underground testing are known and mapped. If a seismic event is located well away from those sites, it is not associated with the test. Even if an event is located within the broader region, its depth, waveform, and timing can be compared with known patterns. Today, there are no underground nuclear tests taking place at the Nevada National Security Site. Monitoring networks in the United States and internationally are designed to detect and identify seismic events worldwide. These networks contribute to verification systems that distinguish natural earthquakes from explosions. The history of testing has also contributed to scientific knowledge of the crust beneath Nevada. Controlled explosions provided data about how seismic waves travel through local rock and sediment. This information helped refine models of wave speed and attenuation in the region. Attenuation means the reduction of wave energy as it travels. By comparing signals from known explosions with those from natural earthquakes, scientists improve their ability to locate events and understand the structure of the crust. In this way, a historical activity left a technical legacy that supports modern earthquake science. For residents of Las Vegas, the memory of testing can shape perception. A brief tremor may lead to questions about human causes, especially when the event feels sudden or sharp. The scientific response remains grounded in measured evidence. Seismometers record the motion. Analysts examine the waveforms. The event is located in 3 dimensions. Its depth is estimated. Its magnitude is calculated. Its mechanism may be inferred. if the characteristics match a natural earthquake. The conclusion is based on multiple consistent lines of data. This process does not rely on speculation or assumption. It is also important to note that past underground tests have long since ceased, and the regulatory and monitoring frameworks in place today are designed to ensure transparency and detection. The presence of a known testing area does not imply ongoing activity. Modern seismic catalogues list events with their times, locations, magnitudes, and other parameters. These catalogues are open to review and are updated as new data are processed. They provide a consistent record against which any new event can be compared. The geology of the Nevada test site region includes faults and structures similar to those found elsewhere in the Basin and Range province. Natural earthquakes occur in that wider area as part of the same crustal processes described in earlier sections. An event recorded near Las Vegas or within southern Nevada is therefore most often understood as part of this natural pattern. The distinction from an explosion is made through the combination of waveform analysis, location, depth, and known operational history. Instruments do not rely on human impression. They measure ground motion in precise units and record the direction, amplitude, and timing of waves. These records can be compared across stations separated by large distances. A natural earthquake produces a signature that fits the physics of fault slip. An explosion produces a different signature that reflects outward pressure. Over many years, these signatures have been catalogued and studied, allowing for confident identification. This capability is part of global monitoring efforts that extend beyond any single region. In the context of an unusual Las Vegas earthquake, the role of this historical layer is to be acknowledged and clarified. It explains why questions arise, but it does not change the underlying analysis. Observations indicate that present-day seismic events in southern Nevada are natural unless evidence shows otherwise. It remains uncertain only in the earliest moments of a small event, before full analysis is complete, whether every detail of its source is fully resolved. Once the data are reviewed, the classification becomes clear. At this level, the earthquake is placed within a known distinction between natural and human-made sources. The Nevada test site contributes to understanding through history and data, while current monitoring confirms the nature of each event. The brief motion felt in Las Vegas is examined through recorded waves and known physical processes, separating memory from measurement and allowing the event to be understood within the broader behavior of the Earth. Seismic detection is the process that turns a brief movement of the ground into a measured event. In the Las Vegas region, this detection depends on instruments placed across Nevada, neighboring states, and wider monitoring networks. These instruments do not wait for people to feel shaking. They record motion continuously, including events that are far too small for human senses. When an earthquake occurs, the first signs appear as tiny changes in the recorded traces. The signals may be weak, clear, complex, or partly hidden by noise, but they carry the information needed to locate the source and estimate its size. A seismometer is an instrument that measures ground motion. In simple terms, it senses how the ground moves relative to a stable internal mass or electronic reference. Modern instruments can detect very small vibrations across a wide range of frequencies. Some are built to record weak signals from distant earthquakes. Others are designed to record strong local shaking without being overwhelmed. Together, they form networks that watch the crust through time. Around Las Vegas, these networks help separate natural earthquakes from quarry blasts, construction vibrations, distant events, and other sources of ground motion. The first task after detection is timing. Earthquake location depends on knowing when different waves reach different stations. A station close to the earthquake records the waves earlier than a station farther away. Primary waves usually arrive first, followed by secondary waves and later surface waves. By comparing these arrival times across several stations, scientists estimate where the earthquake began. The process is like finding the source of a ripple by measuring when the ripple reaches several points. But in the Earth, the paths are three-dimensional, and the wave speeds change through rock and sediment. Accurate clocks are essential. Seismic stations use precise timing systems so that records from distant places can be compared. A difference of even a small fraction of a second can matter for small local earthquakes. The recorded data include time, ground motion, and station location. Computer systems can make rapid first estimates, and analysts may later review the waveforms to refine the solution. This is why earthquake information sometimes changes after the first report. A location may shift slightly. A depth may be adjusted. A magnitude may be revised. These changes are signs of measurement becoming more complete. Magnitude is an estimate of earthquake size based on recorded ground motion and distance from the source. It is not a measure of damage and not the same as intensity. Magnitude describes the energy released by the event. Intensity describes the effects at a specific place. In detection work, magnitude is calculated from instrument records using established methods. For small regional events, local magnitude or related measures may be used. For larger events, moment magnitude is often preferred because it relates more directly to the physical size of the fault slip. Moment magnitude uses the area of slip, the amount of slip, and the stiffness of the rocks, though these details may be estimated from waveforms rather than observed directly. Seismic stations also record background noise. Noise can come from wind, traffic, machinery, ocean waves far away, aircraft, and other natural or human sources. In an urban region, traffic and construction can create vibrations that complicate detection of very small earthquakes. Networks reduce this problem by using multiple stations. A local noise source may appear strongly at one station but not at others. An earthquake produces a pattern of arrivals across the network. The difference between isolated noise and coherent wave travel is part of how detection systems separate signals from background motion. When an earthquake near Las Vegas is large enough to be felt, public reports can complement instrument data. People may submit observations describing where they were, what they felt, and what objects moved. These reports are organized into intensity maps that show how shaking varied across the area. The maps are most reliable when many reports are available, but they still reflect human distribution. A dense neighborhood may provide more reports than open desert. Instruments provide the physical record, while public reports provide the human experience of the shaking. Instrument coverage affects what can be known. A dense network near an earthquake gives better locations and depths than a sparse one. Stations at different distances and directions help reduce uncertainty. If all stations lie mostly on one side of an event, the location can be less constrained. If stations surround the source, the solution improves. In southern Nevada, regional networks work together with broader systems to locate events, but very small earthquakes can still carry uncertainty, especially in depth. This is normal in seismology and is addressed by careful review. The waveform itself holds more than arrival times. Its shape can suggest the type of source, the direction of motion, and the properties of the path. Analysts can examine whether the event looks like fault slip or an explosion, whether it aligns with nearby aftershocks, and whether its frequency content matches a natural earthquake. Frequency content means the mix of rapid and slow vibrations within the signal. A short, sharp signal may contain more high-frequency energy, a longer rolling signal may contain more low-frequency energy. The recorded pattern helps explain what people may have felt at the surface. Seismic detection also supports early information systems. After a felt earthquake, agencies may publish an automatic location and magnitude within minutes. These first products are useful for awareness but may not include the final reviewed values. Later updates incorporate more stations, improved pics of wave arrivals, and better models. The public may see this as correction, but it is more accurately refinement. Earthquake measurement begins quickly because timely information matters, then improves as the full record is examined. In the Las Vegas area, detection helps place an unusual event into a factual frame. It shows whether there was a real earthquake, where it was located, how deep it likely began, how large it was, and how widely it was felt. It can also show whether additional small events followed. Without instruments, the event would remain a collection of sensations and stories. With instruments, it becomes a measured part of the regional earthquake record. At this detection level, the ground motion is translated into data. Seismometers record waves, clocks align the records, analysts and automated systems locate the source, and public reports add the pattern of felt shaking. Observations can confirm that the event occurred and describe its basic properties. What remains uncertain at first may include fine details of depth, fault orientation, or the smallest aftershocks below detection thresholds. The unusual tremor becomes less mysterious when it's placed on a trace, timed across stations, and read as part of the continuing motion of the crust. Crustal stress lies deeper than the felt shaking, deeper than the buildings, sediments, waves, and mapped surface traces. It belongs to the forces held inside the upper part of the earth, where rock behaves as a strong but breakable material. Stress means force acting within a body of rock. It may squeeze, stretch, or shear the crust. Shear means forcing one part of a material to move sideways past another part. In southern Nevada, the long-term setting is shaped mainly by extension, the stretching of the crust across the basin and range. This stretching does not happen evenly in every place. It is distributed through faults, blocks, bends, weak zones, and older structures that respond in different ways. A rock at depth may look solid and unmoving, but it is never free from force. The weight of overlying rock presses downward. Tectonic motion applies sideways forces across large distances. Temperature and pressure change with depth. Older faults and fractures create planes of weakness. These conditions build a stress field, which is the pattern of forces acting in the crust. The stress field is not visible from the surface, yet it controls which faults are more likely to slip and what type of motion they may produce. In a stretched region, many faults are oriented so that blocks can move downward and apart. Stress accumulates slowly because the crust is strong enough to resist motion for long periods. A fault may be loaded by regional forces while friction holds it in place. Friction resists sliding along the fault surface. The rocks on each side remain locked, even as the surrounding crust continues to deform. This locked state stores elastic strain. Elastic strain means a change in shape that can be recovered when stress is released, like a bent branch springing back. Rock is not as flexible as a branch in daily experience, but over large scales it can store small amounts of elastic deformation. When the fault slips, some of that stored energy becomes seismic waves. The rate of stress loading in the Las Vegas region is slow. It is measured over years, centuries, and longer intervals, not by daily motion felt at the surface. This slow rate is one reason earthquakes can seem sudden. The preparation is gradual and hidden. while the release is brief. The crust may take a long time to load a fault, then release part of that stored strain in seconds. Human attention is drawn to the seconds, not the long quiet interval before them. Earthquake science works to connect those different scales of time. Crustal stress is influenced by the wider motion of Western North America. The Pacific Plate and North American Plate interact far to the west, and their relative motion affects a broad zone of deformation across California, Nevada, and nearby regions. Southern Nevada is not on the main plate boundary, but it lies within the interior region that responds to those broader forces. The response is spread out through many faults rather than concentrated on one line. This diffuse deformation helps explain why earthquakes can occur away from the most famous faults. The stress field reaches across a wide landscape. The orientation of stress helps determine fault motion. If the crust is being pulled apart, normal faults are favored where the geometry allows one block to drop relative to another. If the crust is being compressed, reverse or thrust faults are favored. If blocks move horizontally past each other, strike-slip faults are favored. Strike-slip means sideways motion along a mostly vertical fault. In the basin and range, normal faulting is common because of extension, but local structures may also include sideways components or older faults reactivated under newer stresses. Reactivation means an old fault moves again under a later stress field. Rocks do not all respond to stress in the same way. Strong, intact rock may hold stress until sudden fracture. Weaker rock or fractured zones may slip in smaller patches. Sediment-filled basins may deform differently from crystalline mountain blocks. Fluids in cracks can also affect fault strength, because fluid pressure can reduce the effective force pressing fault surfaces together. Effective force means the part of the pressure that actually helps hold the surfaces in contact. The role of fluids varies by location and depth, and it must be inferred from evidence rather than assumed. In many tectonic earthquakes, stress and friction remain the central controls. Stress changes after an earthquake. When a fault patch slips, it releases stress on the part that moved, but it can increase stress on nearby parts. The change may be small, yet it can influence aftershocks or nearby faults. This redistribution is one reason earthquake sequences occur. It does not create a simple chain that can be predicted step by step. The crust is too complex, and the starting stress conditions are not fully known. Models can estimate how stress may have changed, but they cannot see every small fracture or exact frictional condition below the surface. The crust beneath Las Vegas and the surrounding region contains older structures from earlier geologic episodes. These inherited features matter because stress often uses existing weakness. A fault formed under one ancient condition may become a pathway for later movement if it is oriented favorably. Rock layers that were folded, broken, or intruded long ago can influence how later stress is stored and released. The present earthquake record is therefore shaped by both current forces and older architecture. The crust remembers past deformation through its weaknesses and contrasts. At this inward level, the unusual earthquake becomes a release within a broader stress field. The event is not explained only by where people felt it or where instruments placed it. It also belongs to the long-term loading of faults in an extending region. Observations can measure present earthquake locations, fault mechanisms, and patterns of deformation at the surface. They can support models of the regional stress field. What remains uncertain is the exact stress on each buried fault patch before a given earthquake, and the precise conditions that allow one small area to slip at one moment. Crustal stress is the quiet, stored force behind the sudden motion, held in rock until the balance changes. The rock fracture zone is the innermost region of the earthquake process. It is the place where the stored stress becomes sudden slip, and where solid rock gives way along a surface or narrow band of weakness. At this depth, the city, the desert floor, the basin sediments, and the felt reports are far above. The earthquake begins within rock under pressure, where grains, cracks, minerals, and old fractures are held together by friction and strength. For a long time, the zone may remain locked. Then a small part fails. The failure spreads through the fault surface, and the motion becomes a rupture. Rupture means the breaking and slipping process during an earthquake. It is not always a single clean movement. It can begin at one point and grow outward across a patch of fault. The fault patch may slip by a small amount in a minor earthquake or by much more in a larger one. The size of the patch, the amount of slip, and the stiffness of the surrounding rock help determine the earthquake's magnitude. In a small local earthquake near Las Vegas, the rupture area may be limited, and the slip may be too small to reach the surface. The event is still real because the rock has moved suddenly at depth. Friction controls whether the fault remains locked or begins to slide. The two sides of the fault are pressed together by the weight of overlying rock and by tectonic forces. The surfaces are not smooth. They contain roughness, mineral grains, crushed rock, and small points of contact called asperities. Asperities are stronger spots on a fault that resist motion. Stress can build around them until they break or slip. When they fail, nearby parts of the fault may also move. The rupture grows if the stress released by one slipping patch is enough to overcome friction on the next patch. Inside the fracture zone, rock may be damaged by many earlier events. A fault can contain gouge, which is finely crushed rock produced by repeated movement. It can also contain larger broken fragments, polished surfaces, mineral fillings, and thin bands of altered material. These features affect strength. Some fault materials are slippery. Others are strong and resist motion. Water or other fluids in cracks can change pressure and reduce the force holding surfaces together. The exact condition of a fault patch is rarely known in detail before an earthquake, because it lies hidden beneath the surface. The rupture begins at the hypocenter, the starting point of the earthquake. From there, it may spread in one direction or several directions. The speed of rupture is usually slower than the fastest seismic waves, but still very fast compared with ordinary human motion. As the fault slips, it sends waves into the surrounding rock. These waves are the outward expression of the inner break. The fracture zone itself is small compared with the region that feels the shaking. A limited patch of movement can send energy across a basin, through structures, and into public awareness. The amount of slip during a small earthquake may be only a few millimeters or less on part of a fault, depending on the event size and fault area. A millimeter is a very small length. Yet when it occurs suddenly within stressed rock, it can create detectable seismic waves. The human sense of an earthquake is therefore not a direct measure of visible displacement. It is the response to energy radiating away from sudden motion at depth. A window rattling in Las Vegas may trace back to a small slip far below, amplified and shaped by the path between the rupture and the room. Rock fracture is influenced by pressure and temperature. Near the surface, rock can be brittle, breaking sharply under stress. At greater depth, higher temperature and pressure can make some rocks deform more slowly, but many crustal earthquakes still occur within a brittle upper zone. The depth range depends on local geology, heat flow, rock type, and strain rate. Strain rate means how quickly deformation accumulates. In southern Nevada, earthquakes generally occur in the brittle crust, where faults can lock and release energy suddenly. The fracture zone also has direction. The fault plane may dip at an angle, stand nearly vertical, or curve through the rock. Dip means the angle at which a fault surface slopes into the earth. The direction of slip depends on the stress field and the shape of the fault. In an extending region, the slip may include downward motion of one block relative to another. If older structures are involved, there may also be sideways components. The rupture follows the fault surface available to it, not the straight lines people imagine on maps. At depth, a mapped surface trace is only the visible expression of a three-dimensional structure. Not every stressed fault patch slips at once. Some parts remain locked while others move. Some slip quietly without producing significant seismic waves, a process called aseismic slip. Aseismic means without earthquake shaking. Other parts fail suddenly and radiate energy. The difference depends on friction, rock type, temperature, pressure, fluids, and the rate of loading. In the Las Vegas region, most public attention goes to the sudden events because they are felt or recorded as earthquakes. The quieter deformation, if present, is harder to observe and requires specialized measurements. The fracture process stops when the rupture reaches areas where stress is lower, friction is higher, the fault geometry changes, or the available energy is no longer enough to keep it moving. This stopping process is as important as the beginning. It limits the size of the earthquake. A small rupture stops quickly. A larger rupture continues across a bigger fault area. Scientists study waveforms to infer how rupture grew and stopped. But the full details of a small event may remain limited by the available data. The inner process is real, but it is reconstructed from signals rather than seen directly. At the rock fracture level, the earthquake is the moment of failure inside stressed crust. It is not the rumor, the report, the map, or the sound in a building. It is slip on a hidden surface, shaped by friction, pressure, roughness, fluids, and inherited weakness. Observations can estimate the size, depth, and motion of that slip. They can show whether the rupture fits normal faulting or another mechanism. What remains uncertain is the exact texture and strength of the fault patch before it breaks. The innermost event is brief, physical, and quiet after it passes, leaving only waves, records, and a slightly changed stress field behind. Uncertainty and meaning form the final inward layer of the earthquake. After the shaking passes, the event remains in records, reports, maps, and questions. People want to know what it means, whether it is rare, whether it signals a larger change, and whether the city should expect more. Science answers by separating confirmed observations from unknown details. It does not treat uncertainty as emptiness. It treats uncertainty as a measured boundary around what can be known from the available evidence. A calm interpretation begins with the facts that are most secure, then moves carefully toward the parts that require more data. The first secure fact is that the ground moves when seismic waves pass through it. If instruments record an earthquake near Las Vegas, the event is not only a feeling or rumor, it has a time, a location, an estimated depth, and an estimated magnitude. These values may be revised, but they begin the record. Public reports add information about how the shaking was experienced across neighborhoods and buildings. Together, the instruments and reports show that a real motion passed through the region. They do not, by themselves, reveal every detail of the fault surface, the stress state, or the future behavior of the sequence. The second secure fact is that southern Nevada belongs to an active tectonic region. It is not the most active part of the western United States, but it sits within a province shaped by stretching, faulting, mountain uplift, basin filling, and scattered earthquakes. This setting makes earthquakes possible. It does not make every felt tremor a sign of a major event to come. The region's geology explains why shaking can happen. It does not allow exact prediction of the next damaging earthquake. The difference between possibility and prediction is central to careful public understanding. The third secure fact is that local effects matter. Shaking at one place depends on source, distance, depth, wave path, ground material, and building response. A person who feels a sharp jolt in one neighborhood may be near the source, inside a responsive building, or on ground that amplifies certain waves. Another person nearby may feel less because of a different structure, position, or attention. This uneven experience is normal. It does not require hidden causes. It reflects the physical complexity of earthquake motion as it travels from a buried rupture into the surface world. The fourth secure fact is that small earthquakes are common in active crustal regions, even when they are not often felt. Instruments record many more earthquakes than people experience. A city may seem quiet because human senses detect only a small part of the seismic record. When one event becomes noticeable, it can feel unusual compared with daily life, but it may still fit the broader regional pattern. The meaning of the event depends on measured context, not surprise alone. Surprise is human, context is scientific. Uncertainty remains in several places. The exact fault responsible for a small earthquake may not be immediately known, especially in a basin with buried structures. The depth estimate may carry error. The relation between one earthquake and nearby small events may need further review. The long-term behavior of a fault may be partly known from mapping and past events, but not fully resolved. The stress on a buried patch before rupture is not directly visible. These uncertainties do not erase the observations. They define what remains open. There is also uncertainty in public language. A word like unusual can mean different things. It may mean unusual for a person who has lived in Las Vegas and rarely felt shaking. It may mean unusual in the news cycle. It may mean unusual compared with the local catalogue of recorded events. These meanings are not identical. A felt earthquake may be uncommon in public memory while ordinary in geologic possibility. A small cluster may be notable in a local week while not exceptional in a tectonic province. Clear language reduces confusion by stating the scale being discussed. Earthquake forecasting is another place where meaning must be handled carefully. Scientists can estimate probabilities based on known faults, regional history, and aftershock patterns. They can say that aftershocks are more likely after a larger event and that their rate usually declines with time. They can identify areas of higher hazard over long periods. They cannot predict the exact date, time, place, and magnitude of a future earthquake. This limitation is not a weakness of attention. It reflects the complexity of the crust and the hidden nature of the conditions on faults. Preparedness gives practical meaning without requiring prediction. In an earthquake region, people and institutions can secure heavy furniture, know safe actions during shaking, inspect vulnerable structures, maintain emergency supplies, and design buildings according to seismic standards. These actions are useful whether the next felt event occurs soon or much later. Preparedness is based on hazard, not panic. It accepts that uncertainty exists and responds with steady planning rather than alarm. For Las Vegas, the unusual earthquake becomes a reminder of place. The city is not separate from the desert basin beneath it or the mountain ranges around it. It is built into a geologic setting that continues to move slowly. Most of that motion remains hidden. Sometimes it arrives as a brief tremor. The scientific meaning is not that the landscape has changed suddenly into something unknown. It is that a known kind of process has become momentarily noticeable within a region where such processes are possible. The final interpretation stays narrow and grounded. Observations indicate that earthquakes in and around southern Nevada are part of the natural behavior of the basin and range crust. Records can locate them, estimate their size, and compare them with known patterns. It remains uncertain which small events will be followed by more felt shaking and which will fade into the background catalogue. The questions that follow the Las Vegas earthquake are understandable, but the answers remain measured. The Earth moves, instruments record, scientists compare, and the city returns to stillness with a deeper awareness of the ground beneath it. The city grows quiet again, and the desert surface returns to its ordinary stillness. Roads hold their traffic, lights remain steady, and the mountains keep their dark outlines around the basin. The earthquake has passed from motion into record. It remains in instrument traces, in careful reports, and in the memory of those who felt a brief shifting of the ground. Nothing in the calm scene removes the science beneath it. The valley still rests within a stretched region of crust, where faults, sediments, rocks, and slow forces continue their long work beyond ordinary notice. The meaning of the event settles into proportion. A tremor near Las Vegas can feel unusual because the city is known for brightness, heat, and human activity rather than for earthquakes. Yet the ground below belongs to the same earth as every other basin and range, shaped by pressure, fracture, erosion, and time. The motion is brief, but the setting is old. The questions are natural, and the answers remain measured. What is known stays clear. The earth releases stress through faults. Waves travel through rock and sediment. Buildings respond in different ways. Instruments record what the senses may miss. What remains uncertain is held without fear, because uncertainty is part of careful understanding. The desert does not need to explain itself all at once. It shows only a small movement, then grows quiet again. The valley rests under the night air. The mountains stand around it. The ground is still, not because it is lifeless, but because most change moves slowly. The event fades into the larger rhythm of the region, and the city continues above a deep and patient earth.